You are the guest, I think. Or no, now you can check.
Yes, Pradeep. 1 second. Are you able to see my screen? The slide?
1 second. Yeah, it is loading. 1 second. Yeah, it's good. Um, can you give the print screen? Sorry, full screen.
Full screen, 1 second. Is it
Can
okay?
you change the slides now? Yeah,
Yeah.
it's changing. Yeah, it's okay. Okay, shortly we can start the session at 10 o'clock.
Okay. Thank you. So is it okay? Fine with the
Yeah,
things?
yeah, it's fine.
Okay.
Thank you, Aruna.
Thank you.
Ah, okay. Yeah. Arunas? Check the streaming screen. Your team is streaming. You share your team screen, isn't it? Okay, okay, no issues. Yeah, now it is visible. Okay. Dear participants, the session sharply starts at 10 o'clock. So kindly hold on for others to join. Working as assistant professor, Department of Computer Science and Management Information System at Women College of Management and Technology, Muscat. And she completed her UG in PSG College, Tamil Nadu, and PG at Anna University, Tamil Nadu. And she received PhD award in the Sultan Qaboos University. And he have a more than 7 years of academic and research experience. And her area of interest is image processing as well as the machine learning and data mining, and she give the more contribution to the industrial side and as well as the public domain. It is notable things. She received the third prize in the competition of UCL Summer School Project Exploration at 2020. She providing COVID detection based on the X-ray image. So that is wonderful contribution to the real world. So most of her research is in the medical area. It is for the healthcare institution. So I very much appreciate her work, and I very much glad to hand over the session to the Aruna Devi ma'am. Ma'am, now it is yours.
Thank you. Thank you so much. Good morning, everyone. I'm very happy to be a part of this international seminar. Actually, I have to thankful for the Department of Computer Science, especially Dr. Telagamani, HOD of the Department of Computer Science, and the coordinator, Dr. Pradeep, for giving me a chance to discuss my research and my knowledge with the other students and the faculty members. Thank you very much, ma'am and Dr. Pradeep. And I'm happy for your welcome. You have given a grand welcome for me. Thank you so much, Dr. Telagamani ma'am and Dr. Pradeep. So we'll start with the presentation now. And the first session, it will be like, I'm going to give you the theoretical part and how it will work about the deep learning models. And the second session is about the practical session. We are going to discuss about some few networks like VGGNet and ResNet. And we will use the breast cancer histopathology data that is publicly available Breakers dataset, and we will explore the models, how it will do the classifications. So we'll start the first session. And I have to thank all the participants. Even during the holidays, you are giving your valuable time for this seminar, and you are here. So I'll do my best. I'll share my slides now. Doctor, is it, are you able to see my slides?
Visible, madam. Visible, madam. Visible.
Yeah. Thank you. Today we are going to see the topic deep learning techniques in medical image classification. The outline of my today's seminar is about, first I'll give the introduction about the medical images and medical application and the deep learning concepts. So first we'll discuss about the medical application and the challenges in the medical applications. Then we will move on to the core part of our department, that is the machine learning and deep learning. We'll give some introduction about how it will work, how they will use. Then the more in detail, I'm going to discuss about image classification today. So due to the time limitation, we are going to discuss only about the image classification. And further, I'll move with the CNN convolutional neural network that is applied for the breast cancer histopathology image classification. Then we'll conclude the session. So medical application, I hope you all are aware of these terms. In the earlier days, before, that is 2000 and 2010, the terms that they are using in the medical data that will be very familiar with the people who are working in the healthcare sector. Okay, so during the 2000, they were started with the exploring the medical data. So we are having different, we can obtain medical data in different modality. The first modality, it will be radiology images. the CT images. I hope everyone will be aware of this due to this our COVID pandemic. If you have a cough or fever, the doctor always advised to take the CT images to examine your whether it is COVID or not. And the ultrasound images, then MRI images and the PET images. These images will be coming under the radiology images. Then the other pathology images. Pathology images we will call it as histopathology images. These images that is particularly taken from the patients to diagnose whether the patient is having cancer or not, to diagnose the purpose of cancer. They will take the tissue specimen from the patients and they will do some process to diagnose the images. Okay, diagnose with the images. Then lab medicine data. It is very common in our country that the patients, if you are going for a doctor, then definitely if you are going for a viral fever or anything, they will ask us to take the blood test or urine test. Then they will be observed the test and they will suggest for the medications. So these are all the different modalities we will be obtaining these medical data. I hope you know that the challenges in medical application is the main challenge is the data collection and the interpretability. That is these medical data, it is not easily available for the researchers and for the users and other members. If we want to collect the medical data, then we need to get an ethical clearance from the hospitals. If you want any medical images from any hospital, a PSG hospital or some other government hospital, we need to apply for the ethical clearance since it is confidentiality, because these images are particular to the person. So we need to maintain the confidentiality. So it will not be easily available to us as a researchers. And the interpretability. You can take during the COVID pandemic, we are having an issue. There is the workflow in the healthcare sector. Even though we are having a lot of population and with those who are working in the health sector, it is not, they had a huge workload when they are dealing with the COVID-19 for all the people. So to avoid these things and to reduce their workload, our machine learning and deep learning playing a key role, and the models which are developed recently has a huge performance in identifying a disease and identifying the prognosis of the disease, and also for the treatment purpose, they are doing its best level. And if you consider natural language processing, that is a part of a machine learning and deep learning. If you are giving any report, then easily it will change your report in the PDF format or whatever format, and it will take only the details which is suggested by the doctors, and it will be trained with the models, and it will guide, and it will help the people who are working in the health sector to identify and detailed study about the disease. So first I'll give a basic introduction about machine learning, how it will work, and the drawback in the machine learning. Okay, so I have used a medical image, that is the histopathology images. This is the histopathology images. The term we have used this benign and malignant. Benign, I hope you all know that benign is non-cancer images. Okay, it refers to a non-cancer images, and malignant is cancer images. These images are from the cancer images. Okay, so if you are giving any medical images, first what they will do in machine learning is, first step they need to pre-process these images. Okay, then after pre-processing, then they will apply some handcrafted techniques like histograms and co-occurrence matrices. If it is spatial domain, if you want spatial domain features, then spatial domain means it will be dealing only with the pixels, and transform domain, it will be dealing with the images into frequency. Is it fine, Dr. Pradeep? Is it
yes,
fine?
sir. Yes, sir. No issue. Yes, ma'am. No issue.
Okay, thank you. So the space, if you want the features, spatial domain and transform domain, we will be applying the handcrafted techniques like the histogram and co-occurrence matrices, and we will apply different transforms, Fourier wavelet and wavelet, other wavelet transforms to obtain the features. So when we are obtaining these features will be given to the machine learning model. So the machine learning model like SVM, that is support vector machine, logistic regression, they will learn from these features that are used for training. Then if you are giving any test data, then it will be classifying the test data according to our features, which is learned with the help of the training data. And moreover, I have to inform that if you are using the images, okay, if you are using images, it will be normally all our data will be in the format of zeros and ones, and these images, it will be like a matrix. If you are using a colored images, it will be like we are having 3 channels. The input of your image is colored image, and it will be in 3 channels, that is red channel, green channel and blue channel. We will be dealing with these 3 channels, and these each channels, it will be like a matrix. If you are having 1000 cross 1000 images, I hope you all aware of the pixels of your images which you are taking from your phone or with other digital camera. There will be a pixel. So the pixels represents the size of your images. So if you're having 1000 cross 1000 images, you will be having a big matrix with 1000 cross 1000. Okay. So normally the medical images, it will be like a huge, the size of the images will be huge, more than 1000, maybe around 7000 cross 6000. So we need to process these inputs. So first it will be in the format of matrix. Then we will be having each image, it will be having 3 matrix. Okay. So we need to flatten the matrix when we are going for the pre-processing step. So that you should keep it in your mind. So then we are using feature extraction using handcrafted techniques, and we are giving it to the machine learning model. And we are doing the classification. The main limitation of this machine learning models was that we need a domain knowledge expert to extract these features. So when you are giving a raw data, we need to domain knowledge people to sit and extract this feature, apply this to SVM or logistic regression or random forest, whatever it is, the machine learning models for the classification. So then the deep learning model evolved. Already the neural network, artificial neural network, it was there from the 1960, but it emerged. But it emerged. Yes. Do you want me to?
Kindly participants, kindly mute yourself.
Sir, Pradeep sir, you mute all the participants, sir, from your end.
Yes, ma'am. Thank you.
MRS.
Okay, then I'll move. So to avoid the limitation in machine learning models, the deep learning model was proposed, and the deep learning model was a part of the artificial intelligence, that is artificial neural network, that was already existing from the 1960, but it became very popular due to the high computing powers and the amount of data. We are having a large amount of training data. Deep learning is a subfield of machine learning. You should not think that deep learning is something and machine learning is something. From machine learning, we have proposed the deep learning concept, and deep learning is a subfield of machine learning that will be using the artificial neural network that are very deep. Okay, we will be having multiple layers to learn the data. If you are giving any raw data means if you are giving an Excel sheet or if you are giving an images, okay, whether it is your photo or your the natural images or the medical images, it will automatically extract the features using the hidden layers. They will learn the features and it will be forward to the final layer to classification. This is popular because availability of large amount of data from 2012. I think the ImageNet dataset that was developed and published after training with the huge amount of data, the classification very well. Then there is the availability of high computing power. Now, if you take, we are easy to get the GPU computers, GPU laptops by ourselves in our home itself. Earlier, before 2010, it was very costly. Only the organization and the institutions, they will be having this GPU computing power. Also, the availability of complex algorithms. Complex algorithms, that is, earlier we are using the matrix. Here now, we are dealing with the tensor concepts. We will be having the tensors to retrieve our data and process our images. So I'll give a basic introduction about the artificial neuron. Here,
Participants, self.
Dr. Pradeep, actually, it was removed automatically.
Yes. Yeah, you can proceed.
Yeah. So this is a biological neuron, and it is very similar to the neurons that we are using in our artificial neural network. Here, you can, from the biological neuron, that is how our brain works. From this, they inspired and developed the artificial neural network. Okay, this is the input that enters. It will receive the input and it will perform the operation and it will pass to the other neurons. Okay, in the same way, we will receive the inputs, our inputs here, medical data. Maybe I'm considering more focused on the medical image classification. So images, that is your images. So first image, second image, and if you're going to use 100 images, so the X1 represents the first image and X2 represents the second image, and 100, this Xn represents the 100th image. Okay, and the term which we were using in our deep learning, that is neural network, is this weight. Okay, that will be called as filters. You can, in some term, they will be referring it as filters, and the parameters they will be using. So these are the terms, first input and weights. So then what they will do is each input, that is each image, okay, the first image will be multiplied, that is convolved, that is multiplied with the, do this operation with the weights, that is the parameter, and for each input it will be multiplied with the weights, and we will do the summation for all the values. Then we will feed into the activation function. The main purpose of the activation function is that it will transfer from the linear. So if it is less than 0.5, it will make it 0, and greater than 0.5, the values of each thing, and it will make it as the pixels. Okay, then it will make it as a 1. Then we will feed into the classifier. Then we will get the classification. That is the output of our function. Okay, so I will explain with the, start with the perceptron. This is the first, and also I'll give few examples how it will work. Okay, so the perceptron, the artificial neuron, that is the fundamental unit. Okay, we have seen the artificial neurons. This is the fundamental unit that takes multiple inputs and process those inputs. When you are processing those inputs, each input will be multiplied with its corresponding weights and forward the output to the other neurons in the next layer. Okay, here we are having a perceptron with its input vector. We are having a X. Okay, this X represents different images, X1 until Xn. And the weight vector, we are having the weight vector, and the activation function, sigmoid functions. I'll explain with the example in the next slides. In the perceptron, we will be having n-dimensional input vector and weights, corresponding weights. Each inputs will be multiplied with this weights. Okay, then it will be forwarded into the this summation. We will be doing the summation. Then we will give it to the activation function as we discussed in the earlier slide. Then we will be obtaining the output. So how it will work, if you're having, you have to think how it will work, if you are giving an image. Now I'm giving only the, for the simple way to understand, I have given a simple example how it will work for the single neuron with its one input and a weight. Okay, so X1 we are giving, and our X1 value is 0.1 and the weight value is 0.15. Okay, when you are doing this, and also there will be bias, we'll be adding. So X1, it will be multiplied with the W1. Our value 0.1 will be multiplied with the 0.15. This is the corresponding weight value of this input X1. Then we are adding a bias values to make it stable. 0.415 we will be obtaining as the output of this function. Okay, then we need to forward it to the activation function to make it non-linear. So we are using a sigmoid function. This is our sigmoid function. So 1 by exponential of this W transform and the X plus B, and we are giving this values, and when you are placing this, we will be obtaining the output as 0.603. Either we will, if we are having in another layer, we will be passing this output to the next layer, or if we are using directly the output layer, then we will be using this value to classify the images. Okay, here we are having a single input, single weight values, and we are having a single layer of neuron, single neuron. This is the neuron. Okay, then we need to pass it to the sigmoid function. We have a lot of activation functions like ReLU function, sigmoid function, TANH functions, and nowadays I think GELU functions. You can use whatever you want for your model. The basic thing is with the sigmoid function, it is easy to understand. Then I'm going to explain that if you are having a 2-layer network. Okay, this is the first layer network, and this is the second layer, first hidden layer, and we will be considering it as a second hidden layer. So the same input, we are passing the output which we got from our first layer, that is 0.6023, and it will be passed. This value will be, this is here, okay, output from the first hidden layer of these things. Then it will be forwarded to the next second hidden layer. So we are having a weight 2. It is 0.45. So it will be multiplied with this value, and bias will be added, and then we will be applying the sigmoid functions. Then we'll get the output as A2. Using this, we will be forwarding it to the next layer, or we will use it for the classification. Is it clear with you all? I need some more answer so I can proceed.
Yeah, it's very clear, Aruna. You can proceed.
Okay. So next, we are having different models in our deep learning. Okay, so why I have chosen convolutional neural network? Because convolutional neural network actually give huge attention for the classification. If you go for classification, most of the research papers, they'll be using this convolutional neural network. I think from 2012 to 2020, now we are having an advanced other networks, and there is a hybrid still convolutional neural network performing and giving a good performance for some of the applications. So next, in the coming slides, we'll be discussing more in detail about the convolutional neural network and how it works. Convolutional neural network, it consists of this is the diagram which represents how convolutional neural network will work, how it will be. The outline, there is an overview of that architecture. So it will be having a sequence of convolutional layers, and we will be having a filters. The filters will be convolved with the input images to detect the features at each level, and that will be used for classification. Okay, so we are having a sequence of convolutional layer with the following: pooling layer, fully connected layer, and that will be, we will extract the features, and finally it will be classified. The main difference is there you have if you consider the machine learning concept, we need to apply the handcrafted techniques to extract the features. Then we'll be supplying here the machine learning models like SVM and these things to classify. Here, if you are giving input images, these deep neural networks will learn automatically, and it will classify with the features learned from the during training. Okay. The main building blocks of convolutional neural network is convolutional layer, pooling layer, and fully connected layer. So here I have represented convolutional layer, pooling layer, and the fully connected layer. And in convolutional layer, the main things they will concentrate at how many number of layers we are going to use, and how filters, how many number of filters, and what is the filter size we are going to use. The filters, I am using the term weights. Okay, don't think that is I'm using a new term. I'm going to refer the weights as a filters. So number of filters and the filter size and stride. The stride will be the position which we are moving from during the convolution operation. Okay. We are having an activation function from transforming the input images in the input, our input from the linear to non-linear. Then we will extract the features, and we will be forwarding it to the pooling layer. Here there is no filters. Okay, keep it in your mind that you remind that about that we don't have any parameters in the pooling layer. It is the main work to we will apply the pool window and we will get the features. That is, we will reduce the size of the feature maps. So when we give the input images, what will happen is we will be giving it to the convolutional layer. In this convolutional layer, we will be having a filters and it will be convolved and we will be getting the output that we will call it as a feature map. Okay, the feature map is the output from the convolutional layer, and this feature map will be forwarded to the other layers and we will get another feature maps. And finally, we will be feeding into the fully connected layer. Here I have represented two fully connected layers, and it will be a dense layer. It will be like a flattened one. When we are getting a feature maps from a pooling layer, we will flatten the inputs and we will process for the classification. So more in detail, first I'll explain about the convolutional layer. Convolutional layer is a set of filters that will be convolved with the input images or the feature maps. If it is the first convolution layer, it will be dealing with the filters will be convolving with the input images. Okay. If it is the second, third, fourth, and these convolution layers, that will be convolved with the feature maps. When you are having the two important key parameters for this convolution, the size of the extracted patches from the input images. Okay. When you are doing what is convolution, that is, we are going to multiply a matrix of weights. If you are going to use a 5 cross 5, that is, you can say it as a filter or weights. This 5 cross 5 matrix, it will be convolved, that is multiplied with the, if you are having an image of 32 cross 32, so this 5 cross 5 will be applied here initially here, and we will be getting an output, and using the stride, that is, we will move with the stride, maybe 1 or 2 per position. Then here it will apply second values we will be getting, and this 5 cross again it will be convolved, and here, so likewise we will be convolving with this 5 cross 5 with this input images. Okay, so from the patches, the size of the patches, whether we are going to use 5 cross 5 with the 5 cross 5 image patches from the input image, so we'll be obtaining this. So definitely your size will be reduced here. If you want to make size in the same way, you have to add the padding and all. Okay, so the main important thing is the size of the extracted patches from your input images and depth of the output. Depth of the output here, so if it is a color image, I think I have already mentioned that we will be having 3. Okay, if it is a normal, your photo or your the things which you are taking from the beach or other outside, and if you are taking a rain or some, so your colored images will be having 3 matrices. Okay, so this is the depth. So if I take the input images, the depth of your input image is 3. So in after convolution, the depth of the output, the depth of your, this is the feature map, the depth of the feature map will be based on the number of filters we are going to use. Okay, if you are going to use 64 filters, so this is single image, it is having 3 parts since RGB. Okay, so when you apply the filters, the depth of this single part, it will become, we are going to use 64 filters now. So it will be like we are having, the depth will be 64. Okay, so depth of your feature map for this part, it will be 64, and for that is for the R, red, and if this is red, then it is for RGB, green, you will be having another 64. Okay, so it will be based on the number of filters you are using. So the convolution operation is performed by sliding filters over the input images. Slide, the stride, they will use the term stride, how much you are going to apply the stride. Okay, if you are giving 3, it will move the If you're having an input image, I have already mentioned 32 cross 32. You are going to apply 5 cross 5. So first filter is applied 5 cross 5, that is from 1 to 5, and here 1 to 5. Since it will be in the matrix format, so I'm denoting like this. So when your stride is 3, you will be moving to 1 to 3rd position. Okay. From the 3rd position, the next filter will be applied. Since we are having 64 filters, that is your first filter, it will be applied to all the patches of these images. So this is the first patch and this is the second patch. So this value will be here and the second patch value will be here. Okay. So we will be, after conversion operation, we will be getting like this. The main use of this stride, that how many positions which we are going to shift. Okay, that we are moving from the images. Okay, maybe if we give 5, then there is no overlapping. Here there is a overlapping, that is taking the 4th and 5th column. Okay, and the next and this convolution operation, this is it occupies the most of the computation in the convolutional neural network. Okay, this plays a major role because it is very important when you are doing this convolution operation, and here the features are learning. Okay, when you are doing the convolution operation between the filters and the input images, the features are exactly learned from this operation, and this is the main it will occupy the most of the computation in your convolutional neural network. Next one is non-linearity layer, that we will use the activation functions. Like we have seen in the example, we have used a sigmoid function. I have shown the example of that is 1 by 1 plus exponential of something. So it is we are having different activation functions. We will be using these activation functions to ensure the non-linearity and represent the sparse representation of the feature map. When you say the sparse representation, so there will be zeros in the parts that it is not that it is not important. Okay, if you're having some values, that is in I will write and show, because sparse representation means nothing else. We'll be having more initially our feature map is having some minus point something, minus 003, minus 0.5 and 0.698. So these minus this will be like the features that is not relevant, which is not more, we should not more concentrate on those things. So we will apply the activation functions. If you take the ReLU, okay, normally we will be using nowadays ReLU, and this function, what it will make, if it is greater than 0, it will apply, it will take the input, otherwise it will make it as, if it is negative, there is not a positive integer, then it will make it as a 0. So we will be, our feature map will be more sparse and we will be learning the exact features. And in the first layer, we will be learning the low level features. Low level features means if you are giving any phase or any natural, it will be like an outline, and the edges of your images will be obtained. Then it will be forwarded to the other layers, and it will slowly, here maybe it will be dealing with the eyes and other things. And in the last layer, you will be obtaining the high level features that will be used for the classification. Okay. The next, the main block of convolutional neural network is pooling layer. Pooling layer, usually, normally it will be following the convolutional layer and the activation functions. It will be used to reduce the size of the feature maps by subsampling. So if we will be having different pooling layer, that is max pooling, min pooling. Okay, I will explain with the max pooling. We are having like 12, our feature map, first feature map, okay, like 98, the values are like this, and 4, 6, 66, 112. So we'll be having a big feature map. The size of the feature map is long. I am taking only the 3x3. I'm going to apply the pooling. The pooling size of my pool window is 3x3. Okay. So what it will do is it will take the first 3x3 patches from your feature map. Okay. It will take the first 3x3 patches. Okay. Patches means the sub part of the image. It will take, and I'm going to apply the max pooling. When you apply the max pooling, it will take the maximum of this patch. The maximum of this patch, it will be 121. Okay. So it will take only the 121. And so next, it will be moving straight. You can apply even here to overlap or non-overlapping. It will be moving from 3x3. So it will check the next patch. And it will take the maximum element from this patch. Okay, so I'm repeating again. Here there is no computation. We are not having any filters or weights. We will use the term. Here only we are going to subsample the feature map to reduce the size of the feature map. Okay, here 121 we are getting. But anyhow, we will be learning using the different types of filters, filters. So we will be extracting the features which is very relevant. Okay, so when we are applying the max pooling, sorry, I could not find this. Oh. We will be taking the 121. This is the pixel size. Okay, 12, 13, 98. For your understanding, I have given like this. Maybe if you are seeing and dealing with the images, you will be you can see that is like a 0.001. In even point decimals, you will be having the pixel values if you change it to 0 to 1. So 12, 13, 98. Okay. So from this patch, we are taking the maximum pixel value 121. So we obtain. So for each patch, we'll be obtained like this. So then we will be having the subsample of the feature map. The size will be reduced. Then we will be feeding the feature map to the fully connected layer. There is a last layer which will be learn the features for the classification. Here what it will do is, in the fully connected layer, we'll be having, if you are receiving this feature map, it will be flattened like this. That is a dense layer that we will be using. That it will be like a single column of values. Okay. If you're having like a 32, I can say like 10 cross 10. It will be easy for me to say 10 cross 10. Then you'll be having 100 values. Okay. So these values will be flattened. Flattened means they are converting it to the single column. So we'll be having all the here. And each neuron, that is, we will be calling as each neuron. Each neuron will be communicated with each other neuron, and this will be fed into the classifier. In deep learning models, they'll be using the software classifier. If you want to use the other machine learning classifiers, you can use like SVM, LR also we can use. You can extract the features from this, and we can feed into the other machine learning classifiers. Okay. So the important things, the hyperparameters that is playing major role in convolutional neural network is the number of hidden layers, how many number of hidden layers, that is how much deep your neural networks, and number of filters, whether you are going to use 10 filters, 5 filters in each layer, and in the second layer, maybe you will be increasing 64 filters, and the next layer 128 filters. So how many number of this plays a major role in the extraction of features. And the activation functions, different activation functions are existed in what is suit for our model, and the regularization, learning rate. This is very important. Then that is when you are learning, what will happen is we need to make our error to saturate, at least to reach a global minima. So this learning rate, it will plays the major role. Okay. When you are updating the weight values, it will be updated slowly with the learning rate. And the batch size, we will be giving training the input. We will be giving the input images for the training. So we will be giving as a batch, and we will train the model, and we will learn the features. Number of epochs, that is number of iterations you are going to use it for the training. The next I'll be discussing with pre-trained CNN. Actually, in from 2012, this CNN has become very popular among the researchers since it outperformed the competition, that is ImageNet Large Scale Visual Recognition Challenge. I hope you all know about these terms. That is, they have developed the ImageNet dataset and they have made a challenge competition, and the people, the Professor Jeffrey Hinton and his team, there's Crispy, they developed the AlexNet and they participated, and using the large amount of dataset, that is ImageNet dataset, their error was reduced and they can classify the images very well. Before that, the LeNet was proposed during the year 1998 was Lee Kun, and he was using only the 5 layers. Okay, he was using only 5 layers. The parameters, that is the weight they were using, was 60K, and they were applying for the data, that is the checks. Okay, they want to identify the handwritten checks and they want to classify these. I hope you all know the handwritten digit data set. So we will be using for the training, and we will classify the images. So they were using this data set for this check to recognize the handwritten numbers in the checks, and they attained a good performance. But the research was going on, and the performance was very well when 2012, when they were using the large amount of data set for training, and they classified very well. With the number of layers, they have increased 8 number of layers. In the meanwhile, the next year in 2013, this ZFNet was proposed, and they were involved in the competition, and they reduced the error, and they have changed some changes. They made some changes in the AlexNet. The filter size of 11 cross 11. So if I can say that filter size they will be using was initially 11 cross 11. Then they were dealing with 7 cross 7s and 5 cross 5. Okay, these are all 5 cross 5 matrices filters. That is the weight matrix. Okay, and 3 cross 3 and 1 cross 1. So what they did was this ZFNet, they were changed the architecture of this AlexNet with the 7 cross 7, and also stride 4 changed to stride 2. I hope you can remember, if it is a stride 4, how much position we are moving. Here you can consider this whole my PPT presentation as a picture. So this is my first convolution. So if I'm not doing any non-overlapping, from here I'm doing the next convolution. If it is 3 cross 3, again I'll be, the stride is 1 means I'll be starting from here, and I'm doing the convolution operation. So stride is also important when you are designing a new convolutional neural network, and the number of filters also they varied. Okay. Then next, from the 2014 competition, the GoogleNet, they proposed the Inception network. They will call it as a Inception network. It was developed by the team Segedi. Then they will come. They participated in that challenge, and they performed very well. But the layers, number of layers, they have increased to 22 layers. They have increased in each layer, and also they have they were using different types of filter size. Okay, earlier they'll be using like 7 cross. If it is first convolution layer for the, I'll explain for this AlexNet and this. If it is, this is the second. This is the first convolution layer, second convolution layer. Like this, 8 convolution layer we are having. Okay, so they'll be using the 11 cross 11 for the first convolution layer and for 7 cross 7 for the second convolution layer. Okay, likewise it was they were using, but what the major change what the Google was did with their GoogleNet, that is the Inception network, in the same convolution layer they'll be using 5 cross 5 and 7 cross 7 and 3 cross 3. Even they were using concentrating on each pixel, that is 1 cross 1, that you will be convolving with the each pixel in your image. then all the feature maps will be combined together and it will be forwarded into the next convolutional layer. So when you are doing with the different filter size, you will be extracting different features and it is very efficient. Okay. And this performed well, the Google Net, they won the competition. And the same time, even the VGGNet that was proposed by the Oxford team, that they were using the 16 and 19 layers, and they were using the 3x3 filter sizes. When they were reduced the size of the filters, they were able to learn the features very efficiently. But the Google Net won the competition on this year. Then again, this was improvised and ResNet was proposed with 50 layers. You can see the number of layers that is going very deep from the beginning, LeanNet to the ResNet. Now it is more deep, and number of mobile net and efficient net was proposed. Nowadays, I was listed only up to the ResNet. Okay, that is still giving good results for all the applications. So next we'll go for the deep. I'm going to discuss today with the convolutional neural network that is applied on the breast cancer histopathology image classifications. Before that, I want you to understand what is histopathology, how they are obtaining these images. Okay, histopathology images is the study of their tissues. They will use the tissues to study the disease to identify the presence of cancer or non-cancer. So the histopathology images, it was very essential standard that they will be used by the healthcare sector and also in their research. What they will do is, first they will obtain they will do the biopsy test. If anyone in your family, if you know, then if they have any lump or things, what they will do first thing was, if they will take the tissues, they will take the blood tissues from the patients, and they will do the sectioning and staining process. Okay, to highlight and observe what is going on with the tissues. So this is the process that they will be using for the sectioning, that they will cut and place it in the slides, and then they will apply. Each laboratory will be having different laboratories for doing this, and they will apply the staining. Normally for the histopathology images, if you know, that is, they will H&E stain and also IHE and stain will be used. They will be applying these stains to highlight the cell structure in this tissue. Okay, and finally you will be getting this tissue, and the pathologist, he is a doctor, and the pathologist who is specialized to observe the cells from the tissues, they'll be using the microscope to observe and identify whether the patient is having cancer or not, and also they will identify the stage of the cancer by the cells. So the main characteristic of histopathology images, these images, it will be very large in size. I hope in the beginning of this seminar, I have mentioned this image. It will be in the huge size. So nearly it will be like 40,000 to 60,000 pixels. I hope you can visualize how big it will be. And then it will be obtained in different magnification level, and these images, it will be highly textured. You can see the texture of these images, and there will be color variation and artifacts. The color variation and artifacts is because mainly because it will be obtained from different laboratories. So from different laboratories, so the lighting and everything will be different. Illumination, and the people who are using that tissues, maybe sometimes they will fold and use it. So these things will be happen. The example of this, you can see the normal breast tissue structure. If it is a normal, they are obtaining some, if they found a lump in the breast and they are taking the tissues. When they are looking at this, if it is a normal, it will be looking like this. And this is a breast specimen that is applied after to highlight the structure of the cells that is hematoxylin and eoxylin. This is the stains they have applied on these images to highlight the structures. And here you can see I'm giving examples for this characteristic. Okay, it will be very large in size, and here when they apply the stains, how it will look. And this is the magnification. Here the magnification of 40x. Okay, in different level. If you take a photo, if you zoom and you want to focus a person, or if you want to focus an object, you will zoom. So like the same way, the magnification will be, they'll be doing with the magnification, the microscopes, they will focus more to identify the structures of cells. So this is the basic one, 40x magnification. And when they focus more, it will be like this. And the same image in the 200x magnification, and this is the 400x magnification. Okay, when they increase the magnification scale. And this is the example. That is this Hutchinson stained histopathology images. They will be using different scanners, might be laboratory that they will be using different scanners. So we'll be having the same image with the different view. So these are the characteristic of histopathology images. Generally, it will be like this. So the problem in the manual analysis, histopathology images. So if you know that still we are having not having the facility to deal with this histopathology images and get the result as early as, that is within 2 days or 3 days, we need to send our, if we are in a remote area, we need to give our tissue samples, and we have to go to the city and we have to give, and they will go to the lab. And it will take time, at least a month or 2 months to get the result and process with the doctor, that is a pathologist. Even the pathologist is very limited. And when they are doing that, there will be a chance, there might be a chance for the inter-observable and intra-observable variability. The same person, that is if we are the same doctor, if he is seeing the image, might be giving 2 different decisions. And if you are going with the same image, definitely if we found something and we will not be satisfied, that we want to go to another doctor to discuss and consult to confirm, at least 2-3 doctors if you found any disease, to confirm about it and to process the medication. Okay, and there might be a chance of inter-observable variability and intra-observable variability due to the limited amount of our people in the health sector and the workload. And there will be uncertainty in the decision-making process. Sometimes as a human error will happen, so there will be uncertainties. So our computer-aided diagnosis, that machine learning played a very good role in classification of this task and to reduce the workload of the people. And the main challenge when we are going to deal with the medical images, the main challenge is data collection. As I have mentioned earlier, there will be challenges in the data collection. Okay, it will not be easily obtained from the hospitals. If you go and check for, if you want to move on your research with the medical images. And the next one is how we are going to choose our model. Okay, so what is the architecture we are going to choose for the classification or segmentation detection? So what is the architecture we have to choose? So we have did a review. We found some of the articles that is giving some solution for the lack of labeled data images. And also, if you consider the data collection, you will not be able to get more than maybe around 1,000 or 10,000. More than like imagine it, if you take, it will be like million of images. Okay, if you want to train your deep learning models, you need a large amount of data with a high computing power. Then it will give a more accurate classification. And later on, they have the one which is proposed was the pre-trained networks like LeanNet, AlexNet, GoogleNet, that they will be trained with the natural images, and we will be using it for the medical image classifications. So these then the model selections. These are the main challenges if you are dealing with the medical images. So Dr. Pradeep, we can continue, or we want to give a break for the listeners?
No issues, Aruna. You can continue. We can wind up the session at 12 o'clock and then we can start at the 2.
Okay. What is the time now?
Now it is the 11. You have another 1 hour.
Yeah, okay. I thought they might be feeling tired for the
Oh,
continuous.
okay. You can take, if you need, you can take a 5 minutes break. Okay.
Yeah,
Yeah, you
5 minute
better
break.
take. Yeah, okay. You can
And
take.
we will start with the architecture, and I hope it will go around 15-30 minutes, and we'll finish it.
Yeah, okay. Then.
Okay. So I can take a 5 minute break, and I'll be back.
Sure, Anna. No issues.
Okay.
Can I proceed, ma'am?
Anu, shall we start?
Yeah, yes, I'm here.
Yeah, okay.
So you are able to view my screen? Are you able to see? There is some other. Are you able to see my screen?
No, no. One second. Yes, sir. No, it's visible.
Okay.
Yeah, you can proceed. Kindly participants mute yourself.
Kindly mute yourself. Some of you have switch on.
Yes, I will mute it.
Okay, so let me start.
Yes, sir. No, you can proceed.
Okay, so to address the challenges, how we are going to choose our models that we have done the review, that the mainly focusing on the breast cancer histopathology image classification. We have differentiated into 3 categories, that is manually designed CNN architecture and pre-trained CNN architecture and the automatically designed architecture. First, we will check with the manually designed architecture. Why it is manually designed, I'll explain. So if it is like a convolutional neural network, I hope you know aware of the structure, number of convolutional layers, number of pooling layers, number of fully connected layers, and this each for each convolutional neural network we can do the experimentation and we can vary the layers by ourselves. So we named it as a manually designed CNN architecture. If it is a pre-trained architecture, then they will be using any pre-trained CNN like
Anna, the screen is not visible.
The screen is not visible. 1 second. Can you close? 1 second. Is it visible presently?
No, no, it's not visible. Yeah, it is
No?
loading. Yeah, it is loading. Yeah, it's okay. It's visible. Yeah.
Is it visible now?
Yeah, it's visible now. Can I give the full screen? Yeah, thank you. Thank you.
So we have differentiated the CNN architectures based on manually designed CNN architecture that the people who are working and they were varied the number of layers and number of filters and sorry, pre-trained CNN. That is, they were using the pre-trained CNN like AlexNet, VGNet, ResNet, MobileNet, EfficientNet for the breast cancer histopathology image classification, and the automatically designed neural network architecture. There is a neural architecture search that will design the architecture by themselves, and that they will. This is a current field that is still need to be explored. There was only 2 papers until 2021 end December. We have analyzed this on the breast cancer histopathology image classification. We found only 2 papers that is focused on the neural architecture search. So these are all the papers that are using the manually designed CNN architecture that the researchers that they have done lot of experiments, lot of empirical analysis to find out the architecture with the for their applications and for their data set, and we have given the references of the researchers. So this is the one Cyrusson. He was the one first proposed convolutional neural network architecture for the breast cancer histopathology image classification, and they were using the ICP year 2022 challenge images, that is 50 images. They were extracting the patches and they were feeding into the convolutional neural network with the size of, we are having 4 convolutional layers. That is, as a whole, they are having a 6 layer, 4 convolutional layer that is followed by the 2 fully connected layers, and the pooling layer we have imparted here. Then they were measured the performance using the F1 score. They obtained the performance of 0.78 for the classification. Then this cruise, they proposed a 3-layer convolutional neural network, and they have used the data set from the Hospital of University, their University Hospital data set, and they measure the performance using FN score and accuracy. So mainly accuracy will not be a good term for the medical classification, either medical data classification or whatever it is. So people will be using sensitivity, specificity, and F1 score other for the to denote their good classification. Okay, if you are doing research in your medical images or medical data, with your medical data, try to use the precision, recall, sensitivity, specificity, F1 score, and AUC for showing the performance of your model, that you have to compare that model and your model. Okay, so try to avoid using the accuracy. And the third paper, they were using 3-layer CNN architecture and the ICPR dataset with the 50 images. Since you can notice, they were dealing only with the less images. Okay, less amount of data. Since you know that medical images, it will not be like we can get it like the ImageNet, a million of images. And this paper, they were discussing, they proposed a 8-layer CNN architecture. Litigen. This is also pioneer research in the histopathology images. They were doing in the breast cancer. If you are doing in the breast cancer and prostate cancer, you can refer this author from the Radboud University Medical College. They were doing a good research, and they proposed a 6-layer network, and they were using the medical images from their university medical college, and they were using the term that they were using the AUC, that is ROC AUC. They will be using like sensitivity and specificity. It will compare, and it will give they obtained a good performance of 0.88. That is how far they have identified the positive as positive and how they classify the negative classes. And the next paper which we were discussing, they were proposed 8-layer CNN architecture, 5 conventional layers and 3 fully connected layers. We have seen these fully connected layers, that is dense layers, and they were using the data set, and they have reported the accuracy. Then by this paper, they propose a 6-layer architecture. You can see the architecture, it will be like 6-layer, 2-layer, 3-layer. They have tuned by themselves that they varied, okay, and finalized their model. This then they break his data set. This is the first proposed publicly available breakers, that is a breast cancer data set, and they reported their performances. And I hope you have noticed the difference of how they are using. And when we move to the pre-trained architecture, you can see they were using the pre-trained architecture as we have discussed earlier, the pre-trained CNN, that is AlexNet, ResNet, VGGNet, InceptionNet, that is the GoogleNet, okay, or the combination of the pre-trained networks. So the main, why they were using pre-trained networks, since if medical images will be having very less amount of data, so the classification performance will be, it will not be attained to the highest level. So if we want to give a good classification, then we need to train with the large amount of data, which is not available for the medical field. So they are training their network with the large amount of natural images like ImageNet, CIFAR, after certain layers. After maybe if you're having AlexNet, until 5 layer, they'll be using the weights, that is training the weights with the natural images. Then the last 3 layers, that will be trained with the medical images, and it will be doing the classification. Okay. So this gave a good performance compared to this models. And the first one, as I have mentioned, for the breast cancer histopathology, the BREAKIS data, which is available publicly. You can download the data set and you can continue your research if you are doing with the breast cancer. And they reported the performance of accuracy. And then again, they were changing the architecture of AlexNet and adding the decaf, extracting, they are imparting the decaf feature. And then they improved the accuracy for 40x magnification, 100x magnification. They reported for each magnification. Okay, there are 4 magnification scale of data set is available in this BREAKIS data set. Then this author, they introduced the combination of Fisher vector. Fisher vector is used to extract the features like unencrypted features, and they combined these features with the VGGNet 19 convolutional neural network. So they combined this and they used the BREAKIS data set and they improved the performance for each magnifications. Then this author, you can see that they have combined the REST network and VGGNet. They'll be using the RESTNet and VGGNet, and finally they will combine the features of these two for the classification. And they have reported the performance in terms of AUC and accuracy. So likewise, the other, we can see in the forthcoming slide, the next slide also, they have done lot of research using the pre-trained CNN architecture, since we are having the access of pre-trained architecture with the help of the Python libraries. And there are a lot of research done with this pre-trained architecture, and they have improved the classification performance in each challenge. These are all the challenge data sets. We have to participate in the competition, and they have performed well on this public data set. And the one which was proposed, the 2019, and this, you can see these papers that they will be discussing about this neural network architecture, neural architecture search, and this outperformed. When you are doing this pre-trained architecture and the manually designed architecture, we need to check with the number of filters and number of filter sizes, and how we can add the one more dense layer or not. For this NAS architecture, they'll be designing the number of filters, number of layers, number of filter size, the filter sizes tried, what is the pooling window size, what is the pooling stride size. They will be working a lot to define a structure. If we are giving a data set, they will themselves identify a structure for itself, and it will take the input data and do the classification, and it gave good accuracy. And in terms of AUC also, it performed well on the publicly available. This both data set which I have mentioned, Breakers data set, this is a BASH data set. It is also a histopathology breast cancer data set. Okay. And if you are going through these 2 review papers, you can learn more about the NAS technology. Okay, even you can work on your further research on this NAS technology, since it is a gray area that need to be more explored more on this breast cancer histopathology image classification. This is the 2 authors. They have used this NAS technology on this data set, and they reported the performance, and it was good compared to all other previous models. And for dealing with the lack of labeled, so far we have seen how we can check for choosing the model. So when you are going with the less amount of data set, if you are dealing with the medical images, you'll be having around 100 or maybe around 1000 or more than, I don't think that we will get, because we got only around 200 images. Maybe we will, some of you might get until 5,000 to 10,000. So we will be using publicly available data, or we need to find some other solution for this small amount of data set. So for this, then I hope you can know about the semi-supervised learning. It was used for this lack of labeled data set. Okay, and the person, this Albert Corey, this researcher, they were using the inaccurate supervision on this data set. There are 3 different weekly supervised learning. It was there, that is incomplete, inexact, and inaccurate supervision. Okay, about this author, the researcher, what they were doing was they were giving they have made a platform. They have made a platform like website, and they were giving the input images of histopathology images or other medical images, and ask the user to enroll, and they'll be giving some example, that is like a crowdsourcing platform. Okay, they'll be giving some examples to view, like whether it is a cancer or non-cancer. We will be viewing and analyzing the images, not analyzing, we will be giving some samples of images. We will be looking at those images, and we will see whether, oh, it is a cancer and it is a non-cancer images. Then they will be giving a test images. Then we have to label that image by our observation. Okay, so people will be enrolled in that platform. Maybe some of we will be having some of the people will be expert. They are having a huge knowledge. Expert people like pathologists, those who can label, and non-expert also, they'll be enrolled in the platform, and they'll be giving the images. So with the few labeled images, and with the lot of images which is labeled through the crowdsourcing platform, they were using on this data set, and they reported the performance. And incomplete supervision, that we will be having small amount of labeled, that is supervised learning, that is labeled images, and we will be having different unlabeled images. Then we will correlate with this, and we will perform the operation on this data set, and they reported the performance. Here, this inexact supervision, these 2 data sets, they were these 2 models, these researchers, they were using the public data set, that is a Breakers data set, which is most commonly used by the breast cancer researchers. And it is like a multiple instance learning. They were using the technique named multiple instance learning. Okay, so they will not take the entire image. They will consider the entire image, and they will make it as a bag, and each bag will contain the patches of images. So with the bags, they will apply their model, and they will classify the images. This is one of the weekly supervised learning, and it achieved a good performance. Then the further, the last 2 papers, what they were doing was they were learning. So far we know the process of the filters are learned, and they were applied for the classification. During the learning, they will be applying the back propagation technique to learn the weights. Okay, here they'll be using the principal component analysis for learning the filters. and these filters will be used with the input images, and they'll be convolved with the input images, and they will get the obtain the feature maps. They will forward to the next layers, and they'll do the classification. They have used their own data sets, and reported the performance. Okay, here I have listed some of the publicly available breast cancer data set. These are all the data set and the links that you can access, you can check, and you can access. Okay, that is ICPR data set and TUPAC Breakis data set. It is very commonly used one, since we are having different magnification. Okay, then the chameleon, then the patches from the patch chameleon data set, and the BASH ICAIR 18 data set. Then the Kaggle. From Kaggle also you will be obtaining lot of data from Kaggle depository. You can obtain. These are all the links which you have given. So I'll conclude the session by giving the future direction. What are the things that are very commonly nowadays, and you can explore with those areas. Still, it is not explored in the field of medical data. Not so much. People are exploring, working on this field, but still we need to work a lot to improve. So if you have seen that we have a lot of in the table, that pre-trained models, it was huge. Even though when we are using pre-trained model for classifications, the models are for certain up to certain layers, it was learning features using the natural images. That is entirely different from your medical images. Okay, so you will be having some it will not learn the information very efficiently, since it was using natural images. Recently, that's why they are going for weekly supervised learning. That is with the small amount of data, how we can that is only with the medical images, how we can improve our model to perform it well. Okay, and the main thing they were using for the NAS architecture, there is neural architecture search, and from the 2020 the vision transformer, that was earlier. Maybe you can remember that BERT model. Sometimes if there are people who are working in natural language processing, they'll be using the term like a BERT model. That is commonly used for the if you go for the Google, you are having translate. You can use the French or Arabic, whatever language, it will transform to the Tamil or English. So those things, they were using these BERT models and this vision transformer models. They were the researchers named, I think, Ashish Vaswani. He proposed a model for the computer vision, and it gave a good performance for the image classification. After that, the researchers, they were digging more on this vision transformers, how they can apply on the medical field and all the data. So for the researchers, this will be the new directions. And these are all the reference which I placed for my session. So if you have any questions, we can discuss. And in the second session, we will be discussing about how we can classify the breast cancer data set, that is the Breakis data set. Easily. Thank you very much. Thank you for your time. Even during the raining time, you are here and listening. Thank you so much. Thank you, Dr. Tilakmani and Dr. Pradeep, for giving such an opportunity. Dr. Pradeep, are you here? So if you have any queries, we can discuss. And
Anna, I'm here. Dear participants, do you have any questions? You may ask now.
If you want, you can send me a mail also. Okay. If you want to discuss in person.
Otherwise, we can able to join the session at 2 o'clock again. Any participants? If you have any query in the sense, you may ask now.
Or else I'll place it the mail ID to your chat, and you can check and email me. Okay.
Yeah. Okay. Thank you.
Good morning, ma'am.
Yes. Good morning.
Ma'am, this is Bhanupriya from M. Kumarasamy College of Engineering, ma'am.
Yes.
I need to have some clarification regarding that NAS. network architecture search.
Yeah.
When can I justify that my work is under NAS? So I'm working on this area, ma'am. If I am
Okay.
designing my network, how can I
Yeah.
justify that my network is a network architecture which is under NAS category? How can I compare my newly designed network
Yeah.
with
Actually,
already
the
existing
one
network?
thing, the main drawback was the NAS architecture. We need a huge high computation, even though some of our pre-trained models we can work with our GPU laptop. I hope you are aware of this. But NAS also
Yes,
we can
ma'am.
work, but it will take a lot of time. That it is like because of the finding the good filters and filter sizes, it will take at least 2 to 3 days to train it. So it is making like a carbon footprint, and it is not good for climate also. So we need to define our model that is giving good performance, and training is within a shortest period of time. So you can justify in that way. If your model is training within 5 hours or 10 hours, you and also you can access the NAS method in the Python library, and you can perform the experiments for your data set, and you can compare that model. Is it clear?
Thank you so much, ma'am. Yeah, I got clarified, ma'am. Thank you so much, ma'am.
Thank you so much for your time and for listening my lecture.
Any other participants?
Hello, ma'am. Good morning.
Yeah, good morning.
This is Shanmugapriya from Kadar College, ma'am. Ma'am, actually, I'm working in the concept of digital signature, ma'am.
Okay.
Will this CNN will work out for that digital signature
Yeah.
concept, ma'am?
Definitely all your images, whatever you are using, it will be work with the CNN and RNN techniques. Now, if you are going with the classification task, it will be working with the convolutional neural network. And if you want to digital signature object detection, you can work with the recurrent neural network. Since I don't have time and I focused only on the convolutional neural network, you can use recurrent neural network and like LSTM. I hope you are aware of that. Yeah.
Yes, ma'am. Yes, ma'am.
Yeah.
Okay,
You can
ma'am.
use combination of that also. Yeah.
Okay, ma'am.
Ma'am?
Yes.
Hello?
Yeah. Yes, ma'am.
Can you able to hear me?
Yes. I am able to hear you.
Ma'am, only one little bit doubt, ma'am. Learning
Yeah.
rate, already logical parameters like patch size, epochs, learning rate, verbose, and everything are there. Yes, ma'am. Epoch in the sense number of iterations the loop is running. After when the architecture is running. And then when the patch size in the sense how many number of input is going towards input. That is called as patch size. Next, by learning rate, ma'am.
Learning rate வந்து நீங்க வந்து vary பண்ணுவீங்க. Sorry for using my language, only for explaining it. Actually, learning rate it will be like நீங்க வந்து 0.12 like you can vary. When you make it slower, it will.
ரிசர்ச்ல போடும்போது 0.1 0.001 அந்த மாதிரி பாயிண்ட்ல இப்போ வந்து நம்ம எடுத்தோம்னா 10 எபோக் எவ்வளவு வருது 20 எபோக் எவ்வளவு
அது நீங்க பண்ணலாம். இன்னொன்னு என்னன்னா கிரிட் சர்ச்னு ஒண்ணு இருக்குதுங்க. நீங்க அது யூஸ் பண்ணீங்கன்னு வச்சுக்கோங்களேன், அதுல போட்டீங்கன்னா உங்களுக்கு அதுவே வந்து சூஸ் பண்ணிக்கும். அது அந்த கம்பேர் பண்ணிக்கும். உங்க இதுக்கு வந்து எது வந்து லேர்னிங் ரேட் கரெக்டா இருக்கும் அப்படின்னு அந்த கிரிட் சர்ச் யூஸ் பண்ணீங்கன்னு வச்சுக்கோங்களேன், ட்ரெயின் டேட்டா ட்ரைனிங் அந்த லேபிள் நீங்க கொடுத்தீங்கன்னு வச்சுக்கோங்களேன், இந்த இது கொடுக்கும்போது ஆட்டோமேட்டிக்கலாவே அதுவே சூஸ் பண்ணி உங்களுக்கு கொடுக்கும் எந்த இது வந்து பெஸ்டா இருக்கும் இந்த ட்ரைனிங் டேட்டாவுக்கு அப்படின்னு. So if you are using grid search, then it will be more. It will give you the result that which learning rate will be suit for your data set.
Okay, ma'am. Learning rate வந்து grid search, ma'am. GRID grid அப்படின்னு கொடுக்கும்.
Yeah, ஆமாங்க grid search. ஆமா. Yes.
Grid search. இப்போ வந்து மெத்தட் நேம் போட்டு அப்படியே அந்த நம்ம லாஜிக்கல் பாராமீட்டர்ஸை நம்ம எழுதிடுவோம் மேம். வேலிடேஷன் ஸ்பிட் எவ்வளவு, வெர்போஸ் எவ்வளவு அப்படின்னு சொல்லி நம்ம கரெக்டா கொடுத்துருவோம். அதுல கொடுக்கும்போது நம்ம என்ன செய்யறோம், லேர்னிங் ரேட் வந்து கொடுக்கும்போது நம்ம அதுல என்ன அதான் 0.2 வருது.
சவுண்ட் கேட்கல கொஞ்சம்.
அப்படியா மேம்?
இப்ப கேக்குது சொல்லுங்க.
அந்த 0.01 0.001 இந்த மாதிரி இந்த பாயிண்ட் வேரியேஷனே கொடுக்கிறதுக்கு ஏதாவது ஸ்பெசிபிக் ரீசன் இருக்கா மேம்? அவ்வளவுதான் மேம்.
ஸ்பெசிபிக் ரீசன் அதாங்க. நீங்க வந்து அது குடுக்கும்போது என்ன ஆகும்னா, உங்களுக்கு வந்து இந்த ஆக்சுவலா எனக்கு அந்த பேக் ப்ரொபகேஷன் அல்காரிதம் டிஃபைன் பண்ண முடியல சின்ஸ் எனக்கும் டைம் இல்ல எல்லாம் இது பண்றதுக்கு. சாரி ஃபார் தட். இப்ப பேக் ப்ரொபகேஷன் அல்காரிதம் நான் இது பண்ணேன்னு வச்சுக்கோங்களேன். வெயிட்ஸ் இந்த ஃபில்டர்ஸ்னு சொல்றோம்ல, அதெல்லாம் அப்டேட் ஆகணுங்க. ஒவ்வொரு எபாக்ஸுக்கும் உங்களுக்கு அப்டேட் ஆகும். எந்த லெவல்ல வந்து அது அப்டேட் ஆகி அந்த ரெடியூஸ்னு உங்களுக்கு இப்போ ட்ரெயின் ஆகும்போது உங்களுக்கு நம்ம எபாக்ஸ்னு காமிக்கும்போது வேலிடேஷன் லாஸ் இந்த மாதிரி காமிக்கும். அப்புறம் ஒரு லாஸ்ன்னு ஒண்ணு காமிக்கும் பார்த்திருக்கீங்களா? அந்த லாஸ் வந்து ரெடியூஸ் ஆகிக்கிட்டே இருக்கணும். அந்த ரெடியூஸ் ஆகுறதுக்கு மெயின் ரோல் வந்து இந்த லேர்னிங் ரேட் தான் ப்ளே பண்ணும். ஏன்னா அந்த கிரேடியன்ட் கண்டுபிடிப்போம், அந்த டெரிவேஷன் ஒண்ணு கண்டுபிடிப்பீங்கல்ல, டெல் எரரோ வித் ரெஸ்பெக்ட் டு டெல் டபிள்யூன்னு ஒண்ணு இருக்கும்ல, டபிள்யூ அப்டேட் பண்றதுக்கு அந்த ஈக்குவேஷன்ல அந்த அந்த டெரிவேஷனுக்கு முன்னாடி பாத்தீங்கன்னா அந்த லேர்னிங் ரேட் n மாதிரி ஒரு சிம்பிள் ஈட்டா சிம்பிள் வந்து யூஸ் பண்ணிருப்பாங்க. அது வந்து உங்களுக்கு எந்த லெவலுக்கு ஸ்லோவா அது வந்து மேக் பண்ணி, ஏன்னா உடனே உங்களுக்கு போயிருச்சுன்னு வச்சுக்கோங்களேன், மேபி நீங்க கரெக்டான ஒரு குளோபல் மினிமம் ரீச் பண்ணாம வேற இடத்துக்கு நீங்க போகிறதுக்கு வாய்ப்பு உண்டு. சோ அதுக்காண்டிதான் அந்த மாதிரி கொஞ்சம் உங்களுக்கு அந்த வேரியேஷனே அவங்க பண்றாங்க.
சரி மேம், சரி மேம்.
ஓகேங்களா? கிளியரா சொன்னேன்னா ஐ ஹோப் சோ.
இல்ல மேம், புரியுது மேம். இப்ப லேர்னிங் ரேட்னா எனக்கு வந்து நான் படிச்சது வந்து லேர்னிங் ரேட் வந்து எனக்கு கரெக்டா அண்டர்ஸ்டாண்ட் ஆகல. இப்ப எப்போக்னா புரியுது, இட்ரேஷன் புரியுது. பேட்ச் சைஸ்னா சில சமயம் பேட்ச் சைஸ கூட்ட வேண்டியது வருது, சில சமயம் குறைக்க வேண்டியது. கூட்டினா சில சமயம் அக்யூரசி நிறைய, சில சமயம் குறைச்சா அக்யூரசி நிறைய வருது. இப்ப யூனிட் மாடலுக்கு பேட்ச் சைஸ் வந்து நான் 10 கொடுத்திருந்தேன். ஆனா செக்மெண்ட் யூஸ் பண்ணும்போது பேட்ச் சைஸ் நான் 2 தான் மேம் கொடுத்திருந்தேன். 10 எடுக்கும்போது அது இமேஜ கரெக்டாவே எடுக்கல. செக்மெண்ட் ஆகி வரும்போது ரிசல்ட்டே வரல மேம்.
ஏன்னா என்ன பாத்தீங்கன்னா, இப்போ நீங்க வந்து இப்போ இன்க்ரீஸ் ஆகும்போது உங்களுக்கு அது குறையுதுன்னா அந்த லேர்னிங் வந்து yeah actually
can I give my suggestion for this problem?
Yeah
Yeah, you don't adjust the default parameter settings. If you change the default parameter settings, then you are going to get different answer. So if you use a feed forward back propagation neural network called as an Levenberg-Margaret back propagation algorithm, some certain functions are there, activation functions, like some of the functions are there. If we not change the default parameter setting, then you will get the exact answer. The default setting for the epoch is on 1000, and then the learning rate is on 0.001. You are going to get the exact answer, ma'am. You asked on doubt now. Why if you change the learning rate, I'm going to get different answer. Please use the default setting. You will get the correct answer. This is my suggestion for your question.
Okay, sir.
Okay.
Okay, ma'am. Okay.
If you want more, you can email me. Okay. So I'll be giving the details. Okay.
Ma'am,
dear participants, the question.
Arnama,
yeah.
Very nice presentation, ma'am. We are able to understand CNN very clearly, and also good references you have provided, also data set details, ma'am. Thank you so much. Ma'am, we need your email ID, ma'am, so that we can contact, because we thought of working in this area, image processing for breast cancer data sets. So can we get your email ID, ma'am?
Yeah. You can get from Dr. Pradeep. I'll give my official email and my Gmail with Dr. Pradeep. I hope he is having some WhatsApp group. He will place the email ID.
Sure, ma'am. I will share the details in the WhatsApp group.
Okay. Thank you, Pradeep, sir. Can you also share the PPT with us, sir?
Yeah,
sure, ma'am. Sure, ma'am.
Okay, thank you so much.
Thank you. Dr. Pradeep, if I think we can wind up and go back.
Yeah, we will join at 2:00. No issues. Thank you, Aruna. Thank you so much.
Thank you, Pradeep. Thank you so much.
Dear participants, sharply join at 2:00 for the afternoon session. Thank you. Thanks a lot. In the same link, it is going to be used. Thank you.
Thank you.